right, so the most requests were for the ball and the string part B. After that, we'll see what we do next. So if you remember, we did the force diagram and everything yesterday, I believe. I'm just going to do part B. And in part B, we had a diagram that looked like this. And the ball is moving in that direction. I think it's what we had for our force diagram, if I remember correctly. So we all agreed that the tension would be the greatest at the bottom, because not at that point, not only is the string or the tension providing a force to counter the weight of the ball, but also providing enough force for it to go in a circle. So as hopefully is becoming old hat to you, you start with Newton's second law. In this case, I'm going to call up or towards the center of the circle positive. So I have a positive tension minus the weight is going to equal m times a centripetal, since that force acceleration points towards the center of the circle. Yeah, I did. I'll send it out again when I'm done with the problem. You must not have been signed in when I did, or for some strange reason. We'll fix it after this, though. Okay. All right. And so I'm looking for the maximum speed, right? So I'm going to kind of substitute in the main things I know. And since that's a centripetal acceleration, I can replace it with v squared over r from our equation sheet. Right? And so I'm going to have, if I rearrange stuff here, just a little algebra, all times r over m is v squared, and I just need to solve that for v, and I will have it. Good. You have the tension, you have the mass, you know the gravitational field strength because you know you're on Earth. They give you the radius, and now it's just math. Any questions on this one before we move on to doing another one? All right, try the math, and I'll read. All right, so 5.103. You've got a book resting on a table. You have to exert a certain amount of force to get it moving, and then less force to keep it moving, which tells me that the static frictional force is going to be greater than the kinetic frictional force, which is the common case. So that I might actually, in my y, even though it's going to mainly be a two-force diagram, I might start with that fact that the static friction is greater than the kinetic friction. Do you think that's because the normal force changed, or because the coefficient of friction changed? The coefficient changed. I mean, if we changed, like, you know, what angle we were at or something like that, or started lifting up on the book, then the normal force could change. but generally, it's not, the normal force is not going to change like that. So I'm going to do two force diagrams. We'll have the book before it moves. Actually, we can get away with doing one here because in both cases the acceleration is 0, right? So it's not that the forces have changed as much as the how big the forces are changed. So we got the weight down, the normal force up. We're pushing on the book with some force F, and because it's trying to slide or sliding, the table and the book are resisting that change. So you have a frictional force back that way, and no acceleration. So start with part A. In part A, F is, for me, let's see, 2.11 newtons. And I'm going to start with the sum of the forces in the y equals 0. And really quickly get to that the normal force equals the force of gravity, which is mg. Does anyone need me to go into more detail of how I got that back? Yeah, that's the force I'm pushing it with, yeah. Yeah, yeah. Yeah, because it has static and then kinetic, right? Okay. Nope. Okay, so let me back up one step. It's our question. The sum of my forces, I'd have force normal positive up minus gravity equals 0. And then if I do a little algebra, I can get that the two are equal. Yeah. Okay. And then I'll do the sum of my forces in the x. That also equals 0, since we have no acceleration. So I'm going to call to the right positive. So I have F minus F of F equals 0. So whatever force I push it with, that's going to equal the frictional force. Remember that frictional force is one of those kind of smart forces, in a sense. It's only as big as it needs to be. So this would be like the maximum value that it had. If I push with 1 Newton, it would be back with 1 Newton. And then I increase to 1.1, and then it goes to 1.1. It just keeps increasing until we hit this limit of 2.11 newtons. All right? So I can then substitute, I know what F is. Here I have mu force normal. And I know my force normal from up above is equal to my weight in this case. So substituting in everything I know, 2.11 newtons equals mu. I have a 1.86 kilogram book, and I'm assuming we're on Earth, so 9.81 newtons per kilogram. And all I'm left to find is mu. What are the units on mu? Nothing. Unitless. And that's why it's a coefficient. It's just a value, just a number, just a description. No units at all. And so then to do part B, I'm going to start over here just to not waste space. In part B, sum of the forces in the y equals 0. Hopefully you see that leads right away to the normal force equals the weight. And then I do sum of the forces in the x equals 0, just like I did here. And I end up exact same spot, except I don't have a force of 2.11. I've got a force of 1. So I end up with 1.01 newtons equals mu times my 1.8. 6 kilograms, 9.81 newtons per kilogram. Oh, sorry, this should be mu static. It should be mu kinetic. And I end up with mu kinetic equals some other different value. Give it a try. See what you come up with. How do you think, off the top of your head, how do you think those values should compare? Definitely B should be small. I expect about half as big. So, you know, if I got like 0.6 here and I got 0.3 something, I'd be happy. And I go, okay, I think I got it right. Okay, hanging box. Good old equilibrium one. So, in this problem, we know we're looking for the tensions in these two different chords, and we have that we know that the box is just hanging there, so we know the total force on it is going to add up to 0 because it's in equilibrium. It's not accelerating in any way. So actually, I'm going to grab that picture so I don't have to do a better job redrawing it. Let's see. All right. So hanging box. All right, so let's see. I'd have the weight of the box down. I'm going to forget about this little cord here and just assume that these two attach right at the box. I could do that little cord, but it's just going to be part of it. So I'd have, let's call this TR for right hand and TL for left hand. And that's really my free body. That would be what I would need for my Y. The only thing I might do here is draw a little component triangle for TL, because I have a feeling I'm going to do the components of TL. And if that angle is theta, then this angle is theta. So this side would be TL cosine theta, and this side would be TL sine theta. Kind of optional, but at some point I personally I need to see that. So I had some of my forces, right? So let's start in should we start in the X or the Y? Okay. Some of the forces in the X equals 0. In the X, I'm going to call to the right and up positive. So I'd have TR, which would be positive, minus TL cosine theta equals 0. And I can't go any further. Let's see what numbers I know. I don't think I can go any further though. I know the mass of the box, and I know my angle. For me, 54.9. So I can go to as far as TR minus TL cosine of 54.9 degrees equals 0, but I can't go any further at this point from my X direction. From my Y direction, let's see if I can make a little more progress. And let's see, I have TL sine theta minus F sub G equals 0. Oh, okay, so TL sine 54.9 degrees equals mg. So I could say that TL equals whatever my mass is, 22.5 for me, times 9.81 newtons per kilogram, all over sine of 54.9 degrees. Find out my left-hand tension. Yay! There was much rejoicing. Then I can go back from there, and now I know TL, and then I can find what TR is once I find out what TL is. For what? Which one did they ask for first? They asked for TL first. So part A I found here. Right, but then to find the tension of the right chord, I've got to use the tension of the left chord. All right, so we're going to look at car cornering right now. What is the maximum speed at which a car can round a turn of this on a flat road with coefficient stack group between tires on the road is this? Oh, we saw this, remember, not yesterday, because we had yesterday, but at the end of the day, Tuesday, I had that little video clip playing showing the free body of the car. So we're trying to figure out the speed at this, given that exact situation. So, car corner. So I'm gonna draw the side view, like the car, like we were looking at this flat on and the car was going around in front of us. So here's the center of my circle. Here's my car sitting on this flat ground, and the car is coming at us. So I would draw this would be my velocity vector there. So I'd have the weight downwards. I'd have the normal force upwards, and I'm going to have a frictional force inwards. And I'm also going to have because it's going around a corner, a centripetal acceleration. There's kind of two problems in this problem set, almost identical. This one and another one. They're almost exactly like each other. So that would be my free body for this. And so I'm going to do the sum of the forces in the y equals 0, because I'm not accelerating in the y. And I know you guys saw this before I write it, but that would mean the normal force would have to equal the gravitational force, right? Yeah. Then we can go on to, I gotta change the color green. And the x equals ma. So again, I'm going to call towards the center of the circle as positive. So my only force towards the center of the circle is the frictional force. I have m, and my only acceleration is that centripetal acceleration. I know my frictional force That's mu force normal from my equation sheet. My centripetal acceleration is v squared over r. It tells me mu. Oh, wait a minute. mg, I know, m v squared over r. Oh, my masses cancel out. Right? And let's see, I know mu. I know g because I'm assuming car. The only planet I know that has cars is the Earth, so you can assume the Earth. I know r. I think mine was like 69 meters. And then solve for v. What's the mistake a couple of people are going to make? Mathematical mistake. Not square rooting. They're going to solve for v squared and forget the square root. Yep. So just solve for v. All right. 9.81. You've got a car driving, going around a corner, this radius, the speed of this. Oh no, we're not doing 981, we're doing 938. Someone just had a question on 981. So 938. The bucket of water being swung overhead. So you swing a bucket of water over a circle. What speed must the bucket have for it to complete the circle without any water spilling? All right. So one way to read this, rather than water spilling, is to read it as how fast does the water need to be going to stay in the circle? Okay. And so when it's at the top of the circle, what's providing the force to keep it in a circular motion at the top of the circle? Gravity. Gravity is what's providing the force. So if I was to draw the water in the bucket at the top, it would look like that. And it's moving, let's say, this way. So force of gravity on it is pulling it down towards the center. And that's what's providing the force, the net force needed to cause that centripetal acceleration. And the centripetal acceleration, if it doesn't need all that, it's going to cause the water to accelerate downwards linearly. So it's going to cause it to fall out of the bucket if it doesn't need all of that. If it goes faster than the minimum, then the bucket itself is going to have to also provide a normal force on the water to get. This is actually one of the ways they provide weightlessness. All right, it's going over the top when that floor stops pushing on you. Did you have gravity? So in this one, really, what we're looking at here, some of the forces, and we'll say it's in the y direction, although it's not really, because we could use towards the center or something. We have the weight, and that's creating the net force that provides the centripetal force. And so you have mg equals m v squared over r. M's cancel, so it doesn't matter how much water's in the bucket. And you know g because you're on the Earth. I think they tell you r, 1.5 meters. And they're asking you to find v. So solve for v.